All right, so hello and welcome everybody also from my side. So today I welcome you to the very first Symposium session, number 1, which will deal with 3 artist talks given by very young artists heading from very different fields of artistic application. So coming up first, we will be given an artist talk by Quadrature. Quadrature is an artist duo consisting of Sebastian Neitsch and Juliane Götz, and today Quadrature will be represented by Sebastian Neitsch. And Sebastian Neitsch will talk about a project he is involved since quite a while now as part of a Beethoven Fellowship program. So he will talk about the artistic interpretation of extraterrestrial noise using artificial intelligence. So now the field is open to you. Thank you very much.
Yeah. Thank you very much for the introduction. We have the chance to work for 3 years on a very complex project because we got this fellowship by Beethoven, which is and the Podium Festival in Esslingen, and as partners the ZKM, which we are very grateful for. So just short introduction what we usually do. Usually we don't do sound or even music at all, which would be the main topic of this talk and what we try to achieve here. Usually we work much more in the installation field. We build kinetic installations. We always work with real time. I don't think we've ever had any, well, we always work with data and usually with real time. We do a lot of video-based works, a lot of robotic-based works, but we hardly really did sonifications. We did one sonification before Stephen, who's the artistic director of the Podium Festival, called us and asked us if we don't want to have like 3 years and create music. It was super surprising, and now here I am. It's pretty strange for me, and I hope you like what we did so far. So the title is Artistic Interpretation of Extraterrestrial Noise Using Artificial Intelligence. We have 3 years. So this is kind of the first year. I'm talking about what happened in the first year, and we focused much more on the extraterrestrial noise than on the artificial intelligence, because we really want to get our data sorted manually or with our own tools first before we dive really deep into artificial intelligence, deep learning, machine learning particularly. But at the end of the talk, it's not like we didn't do anything. We actually worked quite hard to also train some networks, and I'll show you the outputs at the end of the talk. And even more, your topic title would be Searching for Extraterrestrial Intelligence Using Artificial Intelligence. The idea is a little bit the artistic concept that we try to follow, or also the reason why we do this is not that we really want to find aliens. I mean, it's never aliens, basically. That's kind of what you learn when you start doing anything with astronomy. But the search for it is very interesting. There are a lot of reasons why this is artistically interesting for us. I'm going to dive more into what we actually do technically for this talk. But just as a quick remark, for us it's interesting also with this search for extraterrestrial planets or like the second Earth. Usually what humans do is they look for themselves. And it's hardly to do anything else because it's the only intelligence, the only civilization we know. So there's no other example. And this for us is a quite interesting topic from an artistic point of view. So let's talk about input data. What kind of data do we have or can we use to create anything? And this is a trip we did 2016 to ESO, European Southern Observatories in Chile. This is APEX. APEX is a test telescope for the very famous ALMA cluster. So ALMA is the largest radio cluster in the world currently. It's located on about 5,000 meter altitude in the Atacama Desert in the Andes. And APEX is right next to it. So as you can see, this is Juliana, my partner, who unfortunately can't be with us today. It was very cold, but those guys of APEX, they're very independent. And you can just go there as an artist. They actually stop their observation and showed us how fast the telescope was, and we could ride it. It was really, really nice. And this is a very recent radio telescope. It's not even a super big dish, because what they do nowadays, they have a lot of these small dishes, and they do basically an interference and create a large disk out of that. I'm not going to go too deep into that. And it's purely digital also, which amazed me, by the way. Now, it all started more like this. And why this is interesting for me is because you see how this very first data stream actually looked like. You see this graph on the lower left. And when you see these kind of mountain peaks coming up, this is not because the data changed, it's just because you rotated the telescope. So it's rather just a static signal, but because he changed the rotation according to the wavelength coming in, he kind of gets these things. About radio, one very important thing that a lot of people get wrong: radio is basically light. It's just longer wavelength, and it's not audio, because for a lot of people, radio is somehow audio, but of course there is no audio in space. This is just light, longer wavelength. There's a lot of technical reasons why we started to interpret radio signals as audio, also due to the wavelength. This is why we are kind of used historically to think more of audio when we think about radio, and more about a visual output when we think about, which makes a lot of more sense also, about visual light wavelength. This is also a very, very first graph. They didn't do audio out of this yet. They just did this graphs back then. I'm not sure what this was, by the way. I'm also usually, this is another thing. We're usually not so interested what the data really is. Like, we don't really care. We just care about the aesthetic implementations it gives us. But the main reason why we started to do and work with astronomy is because the narratives and culture and history are really interesting. So this is a very, very famous horn antenna from Penzias and Wilson. And it's famous because this discovered the the cosmic microwave background radiation, which is kind of the afterglow of the Big Bang, and is one of the most important discoveries in radio astronomy ever. And the nice history is, like, they weren't looking for this because nobody knew anything about this. I mean, the Big Bang theory back then, this was in the early 60s, I believe, was still controversial, not like now. It was not like a really accepted theory. And they were just looking for other stuff, actually, but they set it up, they plugged it in, and they had this constant noise. And there were actually pigeons living in this telescope, and it was full of pigeon shit, basically. And they thought that that is the cause for the noise they have. So they actually, like, they took weeks off, they cleaned the whole thing, they made it look nice, plugged it in again, still the same noise. And then there was actually a theoretician they worked with that figured out that this might be the cosmic microwave background noise, which looks like this. This is not from that telescope, that's a rather recent modern visualization of it. And it's the little temperature fluctuations of the time when, let's say it in a poetic way, the universe became transparent and the photons could fly freely. It's kind of an afterglow of an explosion, kind of, and it's everywhere. And it's also misleading to call it microwave background radiation because it's actually just right now in the microwave length. This was actually visible, that the sky is dark is a rather, in a cosmic time scale, it's a rather recent thing because this was always glowing, but because the little photons, they lost energy, they were kind of, like this is very amateur talking right now, they were basically just going slower and slower and slower. Wavelength basically went away, they also moved away, everything kind of went away, went more to the redshift, whatever, it became more in the microwave, and that's why we actually now have a dark sky, otherwise everything would be glowing. This is everywhere, so you can think of this like a map of the world. This is also why it looks like this. This is just a projection, a classical problem, how to get a sphere into a printer. A lot of crazy stories about this. Another input that we then use is basically NASA gives a lot of inputs that you can have. So we tried basically at the very first beginning, we tried to look out there, what can we get? What kind of input can we get? Recorded input, live stream input, whatever. And this is, so what I did here, I just put a spectrum analysis on top of it, or more like a visualization.
Jovial bow shock.
This is a probe flying into the magnetic field of Jupiter. And it's a shock when the probe hits the magnetic field, the outside. So this is kind of the very first thing we did. And we were not very satisfied. Like the live streams we found were very limited. I'll show another live stream in a minute. Also, the recordings we found were very special from like probes that did special things. Like, of course, I mean, the astronomers that put data up there, they are not really so interested in showing the non-interesting stuff, the normal noise that you usually get, but they're interested in showing you the stuff that is special. I have a video signal problem, unfortunately. And so what we decided is we want to build our own telescope. And this is a picture from Friday, I think. So this is pretty recent. We just ordered this from China. And it was a quite long process to find a telescope that met our aesthetic standards and our budget possibilities. So it took quite long to research and find it. And this is a 2.4 meter dish that you can also separate in 4 quarters so that it's transportable, because we want to do performances and installations with this. So we need to have a possibility to have a big dish, and size really matters when it comes to astronomy. That we can carry around and bring wherever. Now we have to build our feed horn, because this is not the antenna. This is just the mirror. The antenna is actually on the focal point of this thing. And we have to build it ourselves, because the ones we could find to buy for amateur astronomers are all in the 4-point figure and too expensive for us. Then the next thing we tried is, okay, then we get a signal, how to digitalize it. And there's actually an RTL DSL dongle, which is awesome. If you ever want to do stuff like this, just Google RTL. There's a huge community that works with radio and shows you how to get data in, get data out. And here we're using so this is a strong Wi-Fi antenna. That's it. And we're actually looking in a frequency range right now of a German television channel. So this is a German television. And it's on Teufelsberg. So we did this on Teufelsberg because I have a very good friend who has a studio there. Teufelsberg is an old spy facility run by the US and the Britons during Cold War. It's kind of like the highest mountain around Berlin. It was basically built on top of the elite university from the Nazis. So, yeah, super weird stories there. Yeah, okay. So this tells me that I now should show you a live stream. Maybe before I do this. Yeah, okay. Let's see if that's still running. So it's very small right now, but there are reasons for that. So this is a live stream. This is live right now. And there's actually a Meteor coming in right now. So this is a Meteor tracking live stream from North America. The reason why I took this one, because it's the only stable live stream I could find. The way this works is they send a radio signal to the atmosphere, and they actually get the reflection of that. So it's not really extraterrestrial noise. It's more like reflected terrestrial noise, if you want so. You can do the same thing in Europe very easily, and we just ordered an antenna for £60 from Britain that is just built for that purpose by searching, like you go south and you log into 134 megahertz, I believe, and there's a French military system. It's called Graph, like a gravestone, and it's basically sending crazy strong signal to the atmosphere to search for enemy rockets and enemy planes, but you can basically log into that signal, and then you can also track meteors over Central South Europe, and we're actually going to do some performances with this. So the next thing we did with this was then we tried to find, okay, what can we do with this? This is interesting because we don't have machine learning thing running yet. We had some stuff, it wasn't interesting. So what we did is some very simple stuff. We just put, let me see what makes sense. This should work. So we tried that with the, there we go. And then creating notes, and I'm trying to send this to the MIDI piano, which should be working, but this was working a minute ago. I have a backup video. So basically what it is, it looks like this. This is just note to frequency right now. But then when you have a piano, and especially when you have a MIDI piano, like the grand piano upstairs, it becomes really interesting. It's basically just noise that kind of clears out when the meteor comes, because you have to think this tracking works, that it's really just noise when there's nothing. There's like noise everywhere, but when a meteor hits, it's a peak in one certain wavelength. Yeah, there was no meteor on the video though. Maybe I can try to, because this should work. I don't really see a reason why this shouldn't work. I can try another thing. And the idea here was just for us, like we quickly wanted to have outcomes. Yeah? Like we just didn't want to, like we wanted to really see, okay, what's possible. Let's see if this works. So I'm playing back, this is another recording from another flying, doing something. And what I do is I basically just put a threshold to all 88 notes of the piano. And of course I can decide what threshold I have. So if I kind of turn down the original audio file, play from the beginning, to make it a bit louder. You kind of get a musical interpretation of the sky, as I would call it. This is something that also to play this for different. So this is a pulsar right now. A pulsar is a neutron star that moves really, really quickly, and the original signal is something like this. And then when I zoom in and I just have the mapping of the audio, it becomes something like that. So the only thing I do here is I just check the original FFT frequency, so the fast Fourier transform. I see how much data I have. I just map it to where there is data. I actually change this here for every single file I have. I just change the resolution basically. And then I map it to the 88 keys, and that's it. Like, this is all the artistic interpretation I do. And I already kind of like the outcome quite a lot. And it's just pure noise to, MIDI, that's it. And there are two interesting things here. The first one is, that's quite a pity. Like, why do I need all this KI and machine learning when I already like this super, super simple direct application? And the second thing is, but it's also super good if this is interesting, because a lot of AI and machine learning algorithms using sound work based on MIDI. Because MIDI is very easy for computers to, it's a very clear signal, it's very easy to understand. There's been a lot of knowledge about it, so more later on this. But having MIDI and trying to transform noise into MIDI makes a lot of sense if you want to do music based on machine learning later onwards. So weird that the other thing didn't work though. Let me check the time. Okay. So another thing I wanted to talk, so there's another source of data input that is also really important for us, and that is kind of static data. So this is a catalog from the Australian Astronomical Association, and they have this crazy good up-to-date catalog of pulsars that you can find online. It's open source. Pulsars are kind of, I also like to call them failed black holes. They are the most dense objects that we know in the galaxy, except from black holes. And they are basically the remains of dead stars. Dead stars that are, I would say, about 3 times bigger than the sun, approximately maybe. And what happens is when they die and they explode, not everything really has the energy to go away. There's a lot of material that implodes due to gravity. And what happens when, it's like an ice skater, when you rotate like this and you do that, due to velocity and stuff, centrifugal force, you become much, much, much faster. And what happens there is you have an object, the size much bigger than the sun, shrinking to the size of Manhattan, with the mass of the sun. So that's a crazy increase, decrease, whatever. And those objects spin very, very fast. So they can spin up to 1,000 times a second. The slowest one is only once every 11 seconds. And what happens is they have, on the poles, they have this gamma rays. Like, it's all kinds of different wavelengths, actually, but usually like gamma rays of energy kind of floating out, and they rotate. It's like a lighthouse. And when this gamma ray hits Earth, you get like a distinctive. It's like a metronome in the sky. A really funny story. The first time they saw this, they thought it's aliens or the Russians. It was like Cold War. So this thing was called Little Green Man, and the performance we have tonight is all about this data. We only shift through this data. I'll show you some shots of that later. So, with this live stream, we kind of explored it further. The next thing we did is we created a program that basically spits out notes in real time so that we can work with real musicians, which was kind of wanted by Podium Festival. For us, it was like, work with, humans. It's not really our thing, but yeah. And the output was this. So this is kind of visual representation of the data stream coming in. You can actually see her on the lower left. She's on a cembalo. I now hate that instrument because there's like no dynamics. And there's a cello in the gallery, and I love that because he was able to do all kinds of crazy stuff. We're gonna have this performance now using machine learning in May with an organ, and we're not gonna use humans because we found a guy called Mr. Hasenfuss, actually. And he lives in Bavaria, and as an engineer, and he builds these solenoid-driven MIDI devices that you can put onto an organ so that you can MIDI control the organ. And of course, also conceptually, it fits perfectly, and we have our telescope that we put outside on the marketplace and then drive that thing. That's more about... Yeah, I'm gonna jump this. So, also gonna jump this. So what we usually also do with the data in between is we kind of build little things. This is also the pulsars I talked before. It's just every pulsar gets one LED, and it just blinks in the period of the according pulsar. That's it. And the output is something like that. Pulsar radio sound. And the reason I show this is that this is not really related to the program or the whole story here, but we would have not done it without it because we would have not done the research for the data. This is now the project coming up, and I'll give, like the one I showed tonight, I'll give a very sneak preview. So also here, every LED is one pulsar, and we just go through the data sorted by discovery date, and everything is based on the data. We have 3 chapters. We only decide at which position in the data we switch the chapters. But even how fast it goes, when it kind of shifts to the next piece of the data, is determined always by the last star that we are currently playing. So even how fast it goes through, the whole rhythm is based on the data. That's the first pulsar ever discovered right there. Yeah, more on that later. The next thing we did is we wanted to, I'm going to shift this, we wanted to build our own instrument. We wanted a little bit much maybe this year. We wanted also to build our own instrument, and this is a solenoid that is basically circuit to itself, and whenever it hits the plate, which is basically ground, the electricity flows, and the thing is basically always automatically pulling itself away from the whole thing, pushing it away. We built a lot of them with different sound inputs, and we hooked the live Meteor input to this. So you know all the different pixels that I put on this earlier on, I basically put on these little things. I just changed the currency. We just changed the currency per each solenoid plate. And this is right now. This is a Meteor coming in live, and it's kind of like it's a sound installation, kinetic sound installation. And we kind of had to do this because this is what we usually do. Yeah, this is very recent. We just finished this, so the video is quite low quality. It's just on the cell phone. We didn't really finish it properly. Now the main idea is to have this in a circle, and again have the telescope that I showed before in a courtyard next to it. We're actually going to do this mid of January at the Akademie der Künste, and then directly put the live data that we generate and that we don't get from the internet to this installation. So we're currently in a big production trouble. So now finally, machine learning. Machine learning is quite old, actually, at least the idea. It just has a recent hype due to the fact that we can calculate much more stuff at the same time, as probably a lot of you know. I'm not going to go too deep into what neural networks and deep learning, which is the rather recent big step for machine learning, is really doing. I'm going to go more into our original idea, and it's like this kind of image you probably know. This is from Google Deep Dream, and it's very interesting what Deep Dream is doing here. Originally, Deep Dream was a tool for the developers to have a better insight into the closed system of neural networks. And what they're doing here is they're basically training a network to search for dogs or dog puppies. In that case, I mean, also cats would work, something that you have in abundance, that you find in abundance in the internet. And, but then you give it an image that where there's no puppy at all, which is just totally unrelated, and make it search for it, and then kind of do that again and again and again, and also kind of spit out a visual image. There's a lot of more complex stuff there. It has to go back and recursive, whatever. And the input is something like this. So it kind of interpretates dogs into spaghetti. And this, we thought, might be interesting if you want to search for human-based sound in extraterrestrial or very, very foreign, like maybe the most foreign, now I call it noise or sound, even so it's light, that we can have. And also the oldest, yeah, like so the CMB you had is like just after the Big Bang. It's very old, it's very far in every dimension you can think of, very far away from us humans. And now training a network in speech, in music, in any kind of sound that we as musicians, that we as humans are used to, or that we generate, and then try to find similar patterns in this extraterrestrial sound. That is the basic idea. yeah, and now I'm going to show you where we are. So, yeah, noise to speech, because, that was a wrong written. Speech is interesting because we are culturally trained to recognize speech. We try to interpretate speech almost into everything. It's just how our brains work. This is the bachelor thesis by a student of mine, Alexander Morozov, who I asked to cooperate with us on this project. And we just found this pretty much exactly a year ago, and this is the reason why I called him to join.
It's my last day.
And it's trained on Chopin. And it's not perfect. It's more like a style transfer, or. But the thing is, and that's a big thing for machine learning, it works in real time. And this is a big technical challenge for us, actually, that we're really still fighting with. This is an example where he uses ambience of a gallery. And the nice thing is it's kind of quite close to noise. And this is what's interesting to us. So, yeah, the problem with sound and real time is that sound really works on a time scale, much more than an image does. And to create an interesting sound, you kind of need to know what happened before and after. And I'll try to do that in real time. It's a, yeah. But there's a very interesting style transfer RNN. I'm actually gonna try to show it. I should have the link there. By Dmitry Ulyanov that we took and we changed it a little bit. But basically what this does is it does something very different to this. I mean, this maybe if you kind of did a little bit of research in machine learning, you may know this. It's something that got really famous. It's the style transfer. You take an image yourself. You can actually download this as an app. This is actually from a different one. This is actually one that he just explained how this works, and he's also doing it with sound. But you can kind of have your photo look like a Van Gogh image, or take a photo during the day and make it look like it was taken during the night. And this is interesting because you can have a lot of different input and train it on a certain style, and then have that input as an outcome of that style. I don't know if that makes sense. And what we did is we searched for a audiobook that was very, very long, and that had to be a science fiction audiobook about aliens for reasons. And this is a little, oh no, this is, sorry, I'm going the wrong way. So this is the noise input that we have. Again, a pulsar.
But Taine had been right twice now. The Plumy ship had crept closer by pure trickery, and it was right to remove atomic warheads from the rockets. They had a pure blast radius of 10 miles. To destroy the Plumy ship within twice that would endanger the Nicola and leave nothing of the Plumy to examine afterward. The Plumy ship must have seen the rocket flares.
That's part of the training data. And
And
that's the outcome. And actually, we have quite a lot of quite interesting results depending on different input. But still, of course, when you do this stuff, it becomes interesting when I tell you the story like this somehow. But when I just play this, I'm as artist very unsatisfied. I'm much more unsatisfied than with the stuff I just do, sending it directly to MIDI, for example. So this is a general problem I have, and also a lot of colleagues I talk to. Working with machine learning is difficult because it even actually gives more randomness, uncontrollable randomness to something that, if you have this kind of data, is already kind of random. And the original idea that you have, you will never really get. And you have to produce a lot of stuff, search through it, and then decide what's actually interesting, and then compose it again to something else. But just using machine learning and thinking that you just use this as a tool and get cool, nice outputs, I have never seen that. So this is kind of my personal main learning curve. We are working on a lot of stuff that I don't really want to show yet because it's not so interesting, but promising. So we have two other networks we are working and training on, and in the end what we will do is we will have a lot of different networks running at the same time and basically shifting between them depending on which one is interesting, and also kind of basically creating an orchestra of different networks. That's going to be the plan for, we still have 2 years for now for that, thankfully. Now, noise to MIDI. Maybe before I show the next stuff, there is a very interesting network. Let me see if that works. So this is, of course, from Google, based on Magenta. So what this one does is, it's trained on a youth competition in Japan by Yamaha. It's a Yamaha Grandmasters, and it's currently, to our knowledge, the best training data that you can find. And it's very, it's kind of like the best thing that we can find. And the nice thing about it is that you can send conditionings in real time. So I'm gonna try to do this now and hope it works. So what I'm doing now is I'm basically sending only an A, and the network, well, not anymore. There was a Meteor coming in. I was only sending an A like now, and the network is trying to play something based on the training data as possible only with A's. It doesn't work perfectly, but when you let this run for quite a while, you actually get interesting waves. And as a background, you can listen for this at least very, very often, very long, without feeling very disturbed, which for me is one of the first things that kind of work when working with this sound stuff in real time. Next. So almost done. Then the next thing we did is the files that I showed earlier and that I sent directly to the MIDI, we used a very similar thing. I worked together with Christian Losert, and this is a Max patch, and he just rendered this yesterday for me. And basically it's more like a answer-response thing. But it works with the same RNN, with the same magenta wavenet. And it's also trained on the same data. So what happens here is it's the raw MIDI, just as I showed it before, the raw MIDI from the radio noise coming in, and then you get the response from the RNN, which is again trained on that Grandmaster Piano Youth Competition. This is another version. Which is interesting is that if you minimize everything, the outputs are usually better. So what we do here is we minimize the input. We really map the whole frequency to only 8 keys instead of 88. And then kind of upscale it and then wait for the response. So I showed you a bit more so that you kind of get an idea about the variations you actually get. And I still find it pretty boring, but much better than the very first things we had going on. Yeah, this is basically where we are right now. Thank you very much.
So thank you very much, Sebastian Götz, for your talk. So now I learned that probably LGM number 2, it's the title of your performance.
Yeah.
So probably it means Little Green Man, right?
Yes.
Ah, okay,
Yes.
so thanks for this. Okay, so make sure you show up during the performance, which Sebastian will present later that day at 8 in the ZKM Cube. So LGM number 2 will get its premiere.
Do we have time for questions? Or
We definitely have time for questions. So this is the reason why I now look into the audience, and I'm wondering whether you maybe have some questions for Sebastian. All right, are there some questions? Don't be so shy. So I will hand you the microphone.
Thank you for your talk. I had one question which was thinking about how you scale the pitch to the data, like whether you're just using a kind of linear translation of that part of the FFT window to the 88 pitches of the keyboard or whatever you're doing, or whether you're thinking about weighting that based on compositional decisions, or there would be 100 ways of thinking about other ways of mapping that pitch set.
No, it's very, very direct. It's really just linear. We don't even, what you usually do with FFT, you multiply a little curve on top of it, because of course our ear doesn't hear it the way the FFT does. So you usually have to equalize that. I don't even do that. I don't do anything with the data. I just look, where is the data range? Where do I get peaks? Because as I said, you really, some of the files we had, there was not a full spectrum, like a lot of it was just empty, so I kind of cropped it. And then I just directly mapped the 88 on top of that, linear, that's it. For now.
So Garth, did this answer your question properly?
Yes, but it brings up another one, which is, have you played with the FFT size then also, in terms of thinking about what the gradation of that, where the peaks would be and how close they would be and so on?
Yes, of course, we did that. I mean, for the live Meteor feed and for the grand piano, I actually did a lot of different things like this, like trying to go deeper, higher, also trying to have, like what you can always do is you can kind of say, okay, if a Meteor comes in, have the whole octave shift, just for fun. Things like that. And this I did, yeah.
So are there some more questions coming from the audience?
I mean, unfortunately, a lot of the stuff I didn't record. Like, it was like I just played around, like I just showed you the stuff that I can show you because I recorded it somehow. But probably the most interesting thing were experiments I didn't even record. Yeah.
So what I consider very, very interesting is your approach towards the data, so that you actually are a little bit uncritical towards the actual data that you use, and you just try to make it aesthetic, and you put it on display in quite aesthetic ways. And later during the panel discussion, we maybe can also get behind the question of the data set. Because on many other occasions it's quite important. It's of striking importance, the data you put inside an artificial neural network. So this is just another approach, and later we can discuss also the other approaches which will be brought in by Damian Titsivis as well as Marco Kempf. So I'm seeing there is another question coming from the audience.
The examples where you used artificial neural networks, did you use always a certain state of learning, the learning process, or did you work as well with progressions of learning?
For the speech synthesis, there's different progressions of learning. For the audio magenta, it's a bit closed to me. Like, you really use a finished library, and a lot of things I also didn't really research, to be honest. Like, I'm not so super interested. I also, because I do a lot of real-time coding, but to be honest, I worked with people and I tried to kind of get into the basic theory, but I myself hardly touched any networks, really. I just tried to cooperate with people who were very interested in that. And Yeah, I mean that's it's kind of the problem is also this whole real-time aspect. It's really a big issue for us because you hardly see that. Like usually stuff is rendered, and this core response is kind of one way for us to deal with it. Yeah.
And I was also wondering whether you as an artist felt sort of an urge to actually work with machine learning algorithms now that they are so en vogue or so hip. What is your position towards that? Because during your talk at some point I was under the impression that actually you did not really want to work around this AI topic.
Oh, at the beginning, I was much more enthusiastic. Like at the beginning, I was like, oh, this is what you can do with it, that is what you can do with it. And when you work with data, and we've been working with data a lot, it seemed to make a lot of sense because machine learning algorithms are very good in finding patterns and in interpreting, especially a lot of data. So this seemed like a logical next step for us. Yeah, but I mean, the thing is also that we choose a topic where we had a lot of, we had to learn a lot just to really get live data. So a lot of this year was really also spent on just trying to find out how do I build a telescope. I never built a radio telescope before. I had no idea how to do that, you know. Yeah, a lot of our time was basically just occupied by that, to be honest. And we're really gonna now really dive into it. And then we'll see what my feeling is about. But right now, I'm very skeptical, yeah.
Okay, so thank you very much, Sebastian Götz of Quadrature.